Dear student, so we are going to talk about the sampling distribution and the central limit theorem. To start with, it is important to understand something. What we have been doing mainly in the previous lectures have been descriptive statistics. All right, descriptive statistics. That's what we have been doing in the previous classes. But in the forthcoming classes, what we will be focusing on is what we call inferential statistics. Inferential means what? Inferential means like if the word inferential is like guessing, but in statistics we don't really do guesses, all right? But we will be mainly doing a kind of formal guess, if you want to call it like that. But the formal guess will be, for example, estimation. All right, we will be estimating something. Estimating what? In fact, there will be something that we will call as parameters that we would want to estimate. There are different parameters that you would want to estimate, and these parameters are what we call as unknown quantities. All right, if you want to make it simple, they refer to as unknown quantities. And what are these unknown quantities? Unknown quantities are generally values that you get from a population. All right, let me take a simple example. Let's suppose you are interested in knowing the average salary of individuals in an industry. The average salary of individual in an industry. If you really want to find the exact value of the average salary of individual in the industry, you need the record of all the people in the industry. Let's suppose there are 10,000 or 100,000 or whatever number of people, and then you will compute the mean. But that mean will be referred to as the population mean, all right? And that would have been the exact mean. But I think you would understand that such things are rarely being done. We don't go and collect a data from a whole sample in a general context. That's very rare. We do that. If you do that, we are doing what we call a census. All right, you are doing what we call a census, but this is not something that is done generally for obvious reasons, which I'm not going to discuss here. What we do generally is to take a random sample from this whole population, and the random sample will give me what we call a sample mean, and that sample mean is used to infer the population mean. That is what I'm trying to explain here. There is a difference between what you have been doing earlier and what you are doing now. Now we want to do an estimation on a certain unknown quantity, which is referred to as a parameter. All right, an example here of a parameter would be the population mean, and you will use the sample mean to do the estimate of this parameter population mean, because it is not going to be available in a general context. So to start with, we will make some distinction between these different terms, like population mean, sample mean. We just like we can compute population mean, you can compute the population standard deviation, you can compute the sample standard deviation, and you can compute different measures in these two different settings. So we are going to define certain notations. All right, we are going to define certain notations here. We will have the population measures that we are going to define, and you will have the sample measures that we are going to define. For example, you will have a population mean and a sample mean. You will have a standard deviation for the population and sample, variance, and proportion. Suppose. If we are going to define the population mean, how can we define it? We can define it through the symbol mu, all right, which is a Greek letter, which is used to describe or to define the population mean. And of course, we will have to define the sample mean differently, which is x bar. Bear in mind that the value that you will get from the whole population, if you were to compute the average salary, let's suppose it was 30,000, if you were to compute it, you have to understand that the sample mean will not necessarily be equal to 30,000. It could be equal to 27,000, for example, because it's an estimate of this. All right, it could be some other value, or it could be 30,000 by chance, but in a general context, it will not be the same as 30,000. So this is why you need to understand properly that these are two different measures that we are discussing. And of course, if you have to denote them, you have to denote them differently. One is mu, one is x bar. And what are the notation that we are going to use for the others? For the standard deviation, for example, we are going to use sigma. You are used to this sigma, all right? This is capital sigma in Greek, and small letter sigma is this in Greek, all right? Small letter sigma is this in Greek. And then in the sample case, you will define it as small letter s. For the variance, it's going to be sigma squared. For the sample, it's going to be s squared. I think this is obvious. If this is sigma, the variance should be sigma squared. For proportion, it's going to be p, we are going to define it, and for the sample, we are going to define it as p cap. Now, bear in mind that different books define things differently. For example, certain books define it as pi, all right, and me, I'm defining it like this. So we will take these notation in the context of this course, all right. Now, what is the idea behind what I'm doing here? The idea is to use these measures in view of estimating these population measures. And these measures, we refer to them as parameters. We refer to them as parameters. Whereas these measures, we refer to them as statistics. Be careful, I'm not talking about capital statistics, capital letter S, because this one refers to the discipline, but here I'm talking about small letter s. For example, this one is a statistic. All right, this is a statistic. And this is another statistic, this is another one, this is another one that we are going to use to estimate the parameters, which are defined. Parameters are unknown quantities, all right, that you have. Now understand something. When I'm talking about a statistic, what is the formal definition of a statistic? A statistic is a rule or a formula that you are going to use to estimate a population parameter, a parameter simply. Now, the rule or the formula is a rule or formula that does not contain any parameter itself. The formula that you're going to use for x bar does not contain any parameter itself. And the other thing that you need to understand is that itself, it can be considered as a random variable. And you have already learned what a random variable is. So, for example, if you take x bar, you take the formula 1 upon sum of x to estimate your mu. But this 1 upon n sum of x is a rule or formula that is used to estimate your population parameter, your parameter. And the rule, if you look at it, there is no parameter in it. There is nothing unknown in it, because these are obtained from observations in your sample. These are obtained from observations in your sample. There is nothing unknown in it, so it doesn't contain any parameter. But the other definition of a statistic is that itself can be considered as a random variable. What does this mean? By itself can be considered as a random variable. And this is in fact the purpose of this lecture, is to explain this part, all right? And we are going to get to that in a moment. So just bear in mind, we are moving in a different setting as from today onwards. We are moving from descriptive stats to inferential stats. We are going to lay down a theory, which is the central limit theorem, that will enable us to do inference on large samples, all right? And to be able to do so, we will need to understand certain characteristics of these statistics. However, I'm not going to discuss all of these statistics. I'm going to discuss only this one, which is the mean, the sample mean. We are going to discuss mainly this one. So, what are we going to do here? We are going to illustrate this concept, we are going to consider the other things are relatively simple. I've already been mentioning a few things about that. You can go through it on your own. We are going to consider a situation, an hypothetical situation. To illustrate all these concepts, we are going to illustrate it through an hypothetical situation. I am interested, as I repeat to you, in understanding this x bar. Why did I say that it can be considered as a random variable? To understand this, I will illustrate it through this example. Just imagine that you are considering the salary distribution of in rupees of 10,000 individuals in an industry. So you have an industry, and in the industry you have 1,000 individuals there. All right, you have 1,000 individuals. In this specific case, we are assuming that we know the average salary of these individuals. We are assuming that we know it, and it is going to be this value. We are assuming that we know the population standard deviation, that is the standard deviation of all the 10,000 people, and this is what we get, the standard deviation of the salary of all the 10,000 people. And this one is the average of salary for all the 10,000 people. We are assuming that we know that, but in a general context, these are unknown. But for the sake of explanation, we will say that we know it for you to understand the difference between what we are going to do later on and what is here. So, but in a real context, what happens is that we generally take a sample from that population, a sample of, let's suppose, 100 people. All right, I take it as sample size letter n, small letter n, as 100 people. So this is just a sample out of these 10,000 people. But now understand something. This is based on only one sample that I took. I can get a sample mean when I'm going to compute it. The sample mean that I'm going to compute will not be necessarily equal to this, will not be necessarily equal to that. It might be, for example, 7,900. I don't know what it could be. But listen to this properly. Conceptually, if you think about it well, I have taken one sample, but this the selection of this sample could have been done otherwise. I could have had a different sample. If I were to repeat this sampling procedure, I would have had a different sample. If I had to repeat the sampling procedure, let's suppose I want to renew this exercise, now I could have obtained another X bar. If I did it the first time, I get 7,900. All right. If I do it a second time, if I do it a second time, you don't expect to get 7,900. Now you might get 8,200, for example. Now, this is an hypothetical case. You are not going to take different samples in practice. In practice, you will take only one sample. But we want to illustrate a concept here that will be helpful for inference later on. So try to understand the concept. Hypothetically, you could have had several samples if you think about it well. And if you have several possible samples, it means that you would have had different possible values of x bar depending on how many samples you would have drawn. And if you can have different values of x bar, this means that x bar varies. There is variation in x bar. So x bar, if you understand it well, can itself now be considered as a random variable, and this is why I was referring to it as a statistic. All right, small letter S. I was referring to it as a statistic because it can also be considered as a random variable. Although we are not doing it in practice, we don't do that. It doesn't make sense to take several samples, but try to understand the idea behind it. The idea, the principle is very important because this is something you would understand how the one X bar that you are drawing in practice relates to everything that we are explaining today. So to sum up here, what I just explained, to summarize what I just explained rather, I just wanted to remind you that in a population, you can have several possible samples, all right? And all these several possible samples will not give the same sample mean. Don't forget that our focus is on the mean in this class, all right? We are not referring to the proportion or anything else. So now, what do I want to do? As I just explained to you, you could have had different sample means. X1, 2, let's suppose you take three, let's suppose you have 1,000 samples that you took. One sample thousands out of these 10,000 or 10,000, 1,000 samples you took, right? If you took 1,000 samples, you would have different values of x bar. And if you have different values of x bar, you need to understand that if you were to plot a histogram, you can, if you were to understand what's happening to these values of x bar, you can basically plot a histogram for that. You can plot a histogram to understand what is going on with all these possible values, right? And you will see what is happening. Is the histogram something like a skewed distribution? You can try to study what is going on with x bar. Is the histogram going to be something like a normal? Is the histogram going to be positively skewed? I don't know. You need to ask yourself, is it going to be bimodal? You want basically to study the behavior of x bar then. All right. I want to study the behavior of all these possible values. I want to study the behavior of these possible values. When I talk about the behavior, I'm talking about the shape of a distribution, for example. Shape of a distribution as I just showed you above. Because it is a distribution, you understand why we can have a distribution for it, because x bar is a random variable. It's not a fixed value. If it was fixed, we will not be having a distribution for it. Like for example, mu, we don't have a distribution for mu because it is a fixed value. There is only one population mean. There is no more than one. For the standard deviation as well, there is only one. But for the sample mean, you could have had many. This is why we have a distribution for it. Now, when I refer to the behavior, I'm talking about the shape of a distribution, or I can be talking about the mean of these x bars that I've plotted, for example. So let us try to study the behavior of these x bars. Taking the same example here, that is, I'm going to take the example of salary distribution of individuals in an industry. It's a fictitious data. So what am I going to do here? First of all, you have the distribution that is plotted right before you. This distribution is a distribution of salary. In other words, it is a distribution that we will define as x, excuse me, not x bar, but x. We will define x as a salary, all right? The random variable x represents salary. So what you are plotting right now is the distribution of x. So the distribution of x means if you take the expected value of x, this is what is referred to as mu in this context, and it is 8,778 according to the example. If you take the standard deviation of x, which is referred to as sigma here, this is equal to 3,656. So the standard deviation of x is this, the expected value of x is this. Remember that x refers to your population. But me, what am I interested in? I'm not interested in knowing the distribution of x, but I'm interested in the distribution of x bar. Look at the old difference. There is a difference between x, there's a difference between x bar. X is your salary, but x bar represent your mean salary. X bar represent your mean salary. There is a difference here. Right? We are interested in knowing the distribution of a mean salary. Remember, in practice, we take only one of it, but this one that we took is out of a vast possibilities of X bar that exist. All right, and we are studying not only one of it, we are going to study the all possible X bar. What is the behavior of it? So to do so, listen to me well, and then I'm going to do it for you. What I'm going to do is I will do a simulation, all right, a simulation to illustrate this. Let me explain the simulation, how it will be, and then I will do it for you. I will start drawing samples, all right. The population here is 10,000 population size, which is relatively big. All right, we'll consider it as relatively big. Okay, though it is not necessarily big, but we will consider that as relatively big. It's not bad. What are we going to do? We are going to take a sample of a certain size. Let's suppose I'm going to take a sample of size 10. Let's suppose. So I'm going to choose 10 people randomly. Remember that the selection is random. Without a random sample, all what we are doing is vain. We have to assume that the sample is random. You compute an X bar and get the first X bar. I'll repeat this procedure again. I will repeat this procedure. I'll choose another 10. I will get another X bar 2. We call it X bar 2. I'm going to repeat that procedure for another 10. I'm going to get another X bar 3, and this is going to be repeated many times. All right, that's what I'm going to do. I'm going to repeat it many times. So for the sake of facilitation in terms of my computation, I'm going to select 1000 X bars. Please be careful, it has nothing to do with the sample, the population size here. I'm going to take 1000 samples, and if I took 1000 samples, I will have 1000 X bars. Of course, these 1000 X bar, I'm going to plot a histogram for it to see how the shape looks like. Is it going to be like similar to that, or is it going to be different? But this is only for a specific sample size that I'm referring right now. Then I'm going to repeat this whole procedure and plot a different histogram for another sample size. Let's suppose a sample size of 20. Now I repeat the exercise by taking another sample of size 20. I will have many X bars for sample size 20, and I will repeat this procedure for different sample sizes and see how it goes. So this is what I'm going to do now. Let me do it for you. I'm going to do it through a software that we call R. You don't need to worry about this software. It's not, and you don't need to worry about what I'm going to write down the codes, but just follow the final result. Okay, don't worry about the coding that I'm writing here. I'm just going to give you an idea of what it is. So I've written the codes, and that is what I come up with. I get the salary of individuals in industry A. Unfortunately, I will not be able to write down here, or maybe I could write, but just give me a minute. I'll save it as a PDF, as a JPEG, and then I'll paste it in the PowerPoint file so that we can discuss on it. So I've just run this. I'm going to explain it to you now what is happening here. So here we go. I've pasted it in the notepad, not in notepad, excuse me, but in the PowerPoint, where now you can see a little bit better what's going on. Okay, but we are going to zoom through these different sections to have an idea of what is going on. Let's take this one for example. This one is the salary of individuals in the industry. That is, this one, the top left panel, is the salary of individual in the industry. It is X. It is not X bar. However, when you start looking at the others, like this one, you see that now we are starting to take random samples. I'm taking several random samples from the population, but the sample size is 2. That is, I'm taking several random samples of size 2. Each time I find 2 individuals, I'm going to take the mean salary of the 2 individuals, and I'm going to plot it using an histogram like this, okay, where the horizontal axis represent the average salary for 2 individuals each time. This is repeated for sample of size 3, sample of size 4, sample of size 10, 30, and 100. So that is basically what I'm doing. I'm selecting different samples of different sizes. In each case, I'm taking 1000 samples of size 2, I'm taking 1000 samples of size 3, 1000 samples of size 4, size 10, 30, and 1000. Each time, 1000 sample of size 100. Each time I'm taking that. And I plotted this histogram to see the behavior of these X bars, because remember that now for the sample of size 2, it is as if you have a population of 1000 individuals. But me, what I did, I selected 2 individual, I calculated 1 X bar. I selected another 2 individual, I calculated another X bar 2. I selected another 2 individual here, I calculated X bar 3, and it goes on like that. I did this 1000 times. And when I got all these different sets of values, these 1000 values of mean, I have plotted it on the distribution here. All right, what I've done. And then this is repeated for a different sample size of 3, or a different sample size of 4, and so on. So if we take a look at these sample of size 2, if first of all, before we proceed, just have a look at the scale. I have kept all scale fixed. I have not changed the scale. All start from 0 to 4 to 40,000 rupees. None of them has changed. Why? Because we want to compare what is going on between these different X bars, all right? And to be able to compare, we have to keep the scale similar for each case. So when we talk about the sample of size 2, we try to understand what's going on. Maybe I'll zoom on it first and then we can discuss. Let's take X. This was X. What this is about is X. But then you have here, this is X bar. Anything that comes afterward represent X bar. This is X bar, this is X bar. All that comes afterward are X bar. But this is only is X. It's the one that you saw in the previous slide, in the PowerPoint slide that I gave you earlier. Now, look at this carefully. When the sample size is small, n is equal to 2, you will observe that there is not much difference in the shape compared to the original population distribution, the distribution of X. When the sample size is small, again, you see that there is still this small skewness. Let me zoom out now. There is this skewness always, even for a sample size of n is equal to 4. But as n is increasing, n gets to 10, n gets to 30, n gets to 100, you would observe that this skewness has disappeared completely. Previously it was like this. Oh Lord, excuse me, trying to get this right. So previously it was something like this. It's positively skewed, but then for this one as well, we see that it is still positively skewed. This one as well, still a little bit positively skewed, and so on. But when you come to these one, you will see that there is no skewness at all for these larger sample. So let's make some observations. The first observation is that if you look carefully, let's take some observations. One is just in terms of the shape, as you saw, but let's come back to the observation one by one. There are different observations that you can do in a distribution. The shape, obviously, which is quite obvious here, and then you have the measures of location. You have a location, and you have a spread. These are the three things that you would generally talk about in a distribution. There is also kurtosis, which I'm not discussing here, but we are referring to only these three things here: the shape, which is the skewness; the location, which is through the mean, mode, and median, whatever; and the spread, which is obtained through the range or the standard deviation, etc. So we will start by the location, we'll move on to the spread, and then we comment on the shape. Let's talk about the location first. To be able to see the location, maybe I'll zoom on it so that you can see properly. In terms of location, if you look at the mean, it's close to 10,000. Close to 10,000, it's about 9,000, right? About 9,000. We know the exact value. In the previous slide, it was 8,000. In the previous slide, it was 8,800 something, all right? But if you look at it approximately from this graph, you will see that it is close to 9,000. If you look at the same thing here, it is close to 9,000. Here again, it is close to 9,000. It's not like as if the shape, the distribution has moved to the right or the distribution has changed its location. No, it's still the same. It's close to 1,000 in all of these different settings, irrespective of the sample size. The location is the same. That's the first observation. Let's write it down. The different first observation is that the locations are the same. That's one thing. That is what we observed. The next thing that we observe is what? The next thing that we observe is in terms of its spread. Let me just write it down here. When you look at the spread, the data varies from 0 to 4,000 over x, but we don't need to worry too much about x. We are interested in x bar. But here, look at x bar. The range of values now lies between close to 0 up to 20,000. The more you increase the sample size, look at what is going on. The range keeps on decreasing. The range keeps on decreasing. I think you understand what I mean by range. Range is a measure of spread anyway. And you see that the spread seems to decrease each and every time the sample size is increasing. So we can see that the next observation is spread is decreasing, decreases, as sample size increases. Look at this well. When we talk about location, location is same, irrespective of n of sample size. But here, the spread is decreasing when the sample size is increasing. There is a relationship between these two, but in the location, there is no relationship there. And the last comment is the shape. The last comment is the shape. You observed that in the beginning, look at this carefully, when the sample size is small, the shape looks still skewed a little bit, right? Even for n is equal to 10, there is still this small skewness. But then when you go for n30, n100, for biggest values of n, you would see that there is no more skewness. And the shape becomes, it looks mostly like a normal distribution because it looks like a bell-shaped curve. If you try to plot a line over it, you will see that it looks like a bell-shaped curve, all right? I prefer not to draw it, I'm not an artist, but you understand the idea is that if you try to draw a curve over this here, if you try to draw a curve over these histogram, you will see that it will look like a normal distribution because it's going to be bell shape, and this is going to be bell shape as well, like a normal distribution. So what is happening here? In small sample size cases, I could not say if it is symmetrical, but only when the sample size is large, I could say that they are symmetrical. So what is the next observation? This observation that I'm going to mention applies only if the sample size is large. If the sample size is small, what I'm going to say does not make sense. But what I'm going to say makes sense only if the sample size is large. So what is the next observation about the shape? Is that distribution becomes more like a normal distribution. Distribution becomes like a normal distribution if sample size is large. If sample size is large, only if it is large. If it is not large, this does not apply. Now, how do we summarize all these into only a simple explanation? How do we summarize all these now? To summarize all these, let me just explain that for a different slide. We have seen that the location does not change irrespective of a population size. If you look at the location here, the location was about close to 1000. All right, the location here was about close to 1000. This one as well, close to 1000. The mu here was close to 1000. And for this one, the mean of the x bar, the mean of the x bars are the same as the mean of x. If you look at it properly, the mean of all these x bar are the same as the mean of x. So how can I formalize that in terms of mathematics? If expected value of x is represented by mu, according to what I explained earlier in terms of notation, if the expected value of x is defined as mu, we have understood now, according to the first observation, that the expected value of x bar, that is the mean of x bar, mean of sample means, the mean of the sample mean, which is defined as expected value of x bar. Just because I'm using expected, you already understand that this is a random variable now. This x bar is a random variable. All right, because I'm using the expectation notation here. You understand that x bar is a random variable. So the mean of a random variable x bar is also going to be equal to the population mean, which is mu. That's one of the first observation that I have formalized here in a mathematical definition. Let's take the second notation. Unfortunately, I erased it, but the second notation is about shape of a distribution. Sorry, not the shape, but the spread of a distribution. All right, the second notation was about the spread. We discussed that the spread decreases as the sample size, the spread decreases as the sample size keep on increasing. As the sample size increases, the spread decreases. So what are we going to do? We are going to formalize that in the next slide. The spread decreases as the sample size increases. How do we write this down? This is written down. So remember that the variance of x was defined as sigma squared, or the standard deviation was defined as sigma. When we talk about variation, we understand that the variation of x bar, the variance of x bar, the variance of x bar is happening. What is happening to the variance of x bar? It is, that is, the variation in these different x bars are decreasing when the sample size is increasing. Look at what is the relationship here. The variance of x bar can be defined as sigma squared over n. If you look at this mathematical property here, you would understand that sigma squared is a constant. Just like this, it is a constant. They do not have a distribution in the classical setting, in the classical statistics setting. They do not have a distribution. So if they do not have a distribution, they are fixed. They are considered to be fixed. And if this value is fixed, if sigma is fixed, sigma squared is fixed, try to understand what's going on. As the sample size increases, the whole measure here will decrease. And this is what we observed, by the way. The variance of x bar is defined as sigma squared over n, and this implies that as the sample size increases, the variance of the sample means decreases. That's the second observation that we did. The first observation was that, the second observation was that. The third observation was with regards to the shape of a distribution. The higher, the bigger the sample, if the sample is big, not the bigger, but if the sample is big rather, you will see that the shape looks like a normal distribution. So if you want to have a look at that, we will say that x bar follows a normal distribution if the sample size is large and is large. This is very important because this applies only if n is large, otherwise it doesn't make sense. So these are the three observations that we did. We can summarize all this now into one simple statement. X bar is said to follow a normal distribution with the mean of x bar, which is what we saw here. The mean of x bar is here. Expected value of x bar is mu. So the mean of x bar is mu. And the variance of x bar. The variance of x bar, we just define it here. The variance of x bar is sigma squared over n. All right? It's sigma squared over n. So this is correct only if n is large. I repeat, if n is large. Otherwise, this is not correct because it may not follow a normal, as we just observed. If the sample size are small, they still look a little bit like the population distribution shape. Okay, so what I just showed you in the last statement is basically what the central limit theorem is about. What I just showed you here is basically what the central limit theorem is about. Let me show you the central limit theorem. If you have a sequence of independent, identically distributed random variables with finite mean mu and finite variance sigma squared, then the distribution of x bar minus mu divided by sigma over root n follows a normal distribution, a standard normal distribution. So this one is a different way of writing down what I've just explained. This follows a normal with mean 0 and variance 1. This is what it is telling you here. If n tends to infinity, if n is large, it's another way of expressing the same thing. Here, if you consider this, I can rewrite it differently in the standardized form. Standardized form means x bar, subtract the mean. Remember the case of a normal distribution, subtract the mean, divide by the standard deviation. Our standard deviation is sigma squared, the root of sigma squared over n. So the root of sigma squared over n is sigma over root n, right? The root of sigma squared over n is sigma over root n. And obviously this follows a standard normal distribution because we have applied standardization. The mean will turn out to be 0 and the variance will turn out to be 1. And if n is large, this is the same thing that you will see here, but written differently, all right, expressed differently. That's what the central limit theorem is about. So now, before I proceed further, I just would like to come back to the previous slide where I just explained something. I told you that the expected value of x bar, is mu, and the variance of x bar is sigma squared over n. Now, you might ask yourself, but where did I get that? You understood intuitively what it represents based on the observation. But you have to understand that these can be obtained mathematically as well. So let me just explain that to you now. Okay, let me just explain that to you for you to understand. Before we proceed, we just write it down here. Expected value of x is equal to mu, and the variance of x is equal to sigma squared. I said that the expected value of x bar is also mu, and I told you that the variance of x bar is sigma squared over n. How did I get these? Let's try to understand that for a moment. If we take the expected value of x bar and I want to see if it is equal to mu, is it really equal to mu, or is it just something that we are making up? No, that we are going to look at the expected value of x bar means expected value of 1 upon sum of 1 upon n sum of x. All right. So value of 1 upon n sum of x. Now, the next step is write it down there. This is a constant. We take it out. We get the expected value of the sum of x. I also explained to you once that these two can be interchanged. That is, the expected value of a sum x plus y can also be written as the expected value of x plus expected value of y. What does it mean? The expected value of a sum is the sum of the expected values. So the expected value of a sum is the sum of the expected values. I can write it down like that. If you look at it there, the value of a sum is the sum of expected values. So you have 1 upon n, sum of a expected value of x, and this is expected value of x is what? Expected value of x by definition is mu. So we are summing mu. Now try to understand that mu is a constant and we are summing it n times. It's not written here, but obviously we are taking it n times. Multiplied by n times mu. N disappear, you are left with mu. So this is how we got these values. It's not just a value that is made up. Mathematically, it has been proven that the expected value of x bar is mu, and experimentally, you also saw the same thing in the observation. The expected value of x bar was equal to mu. Now, what about the variance? The variance is defined as the variance of x bar is going to be the variance of 1 upon n sum of x again. And as you know, when you have to take a variance out, what you have to do is to square. If you are having a constant that you have to take out, the constant is squared. It becomes 1 upon n to the squared. So in the word 1 upon n squared. And the variance of the sum of x. Now this is where you have to be careful. The variance of a sum, variance of x plus y, it's going to be equal to the variance of x plus the variance of y under one condition. If x and y are independent. If x and y are not independent, what I've written here is not correct, because there is another aspect, there is another thing that you have to consider, which is the covariance. But in this context, you have to understand that your x are identically and independently distributed as we have stated here. X is a sequence of independent, identically distributed random variables. If they are independent identically distributed, the word says a lot about it. Independent. If they are independent, I understand that the x1, x2, x3 are independent. So if I do variance of x1 plus x2 plus x3 and so on, this can be rewritten as the variance of x1 plus variance of x2 plus variance of x3 onwards up to n. So in a shorthand notation, it becomes the sum of the variance of x. This applies only because x are independent. If they were not independent, this would not have made sense. So it's 1 upon n squared. Do not forget the squared here. 1 upon n squared times the variance, the sum of the variance of x. What is the sum of the variance of x? The variance of x, we defined it as sigma squared. Variance of x, not variance of x bar, but variance of x is the sum of sigma squared. Sorry, sigma squared. So we have a sum here. Of course, as you would have realized, this is a constant. If this is a constant, it's going to be the sum of a constant n times. So it's going to be multiplied by n times the constant that you have. If you have a constant, you are adding n times 1. I is equal to 1 up to n, which is not written here, but of course it's you understand that it is like that. So it is going to be 1 upon n squared times n sigma squared. So if you look at it carefully, the n disappears. You are left with sigma squared over n. This is how we get this formula. And this formula mathematically has been derived, but at the same time, intuitively is being understood. As the sample size increases, the variance is decreasing. As the sample size increases, the variation in x bar decreases. You will see the range is getting smaller and smaller. All right. So this is a little bit about the sampling, the central limit theorem. Just to complete this part, I started with the sampling distribution. I did not mention to you what the sampling distribution means. The sampling distribution is the probability distribution of a statistic. It's a probability distribution of a statistic. If you look at the previous lecture, we talked about different statistics. One of it is x bar, another one is s squared. For example, if you were to plot the distribution of s squared, you will see that you won't get something that is normally distributed, but you will get a distribution which is going to follow what we call a chi-squared distribution. Just for information, it's not normally distributed. So the sampling distribution of a statistic is the probability distribution of a statistic is what we call the sampling distribution. For example, s squared, the sampling distribution is a chi-squared, but I'm not going into the details here. I'm just mentioning it. X bar, the sampling distribution is the normal distribution if the sample size is large. Do not forget that part, if the sample size is large. So we have studied the sampling distribution, what it is. It is a normal distribution if the sample size is large, and this is what makes up the central limit theorem that we just discussed. And the condition is that the sample size is large, and you may ask yourself, what is large? For this course, we will consider n as greater than or equal to 30 to be large. This depends on books, this depends on notations. Things are not the same everywhere, but for this course, we are going to define n is greater than or equal to 30 to be large. I hope this has been helpful, but there is something else that I need to talk about. This last part here. This one. Be careful. I have included it under the central limit theorem title, but it's not really the central limit theorem that I'm discussing here. It's another theorem, but not the central limit theorem. So the central limit theorem we've already explained. We've finished with that. I hope you understood. But the next step is to talk about this small theorem that I've just mentioned here. What does this theorem state? If a distribution of x is your population here, don't forget the difference between x bar and x. There are two different things here. If your distribution of x is normal, now before I move on to this one, just remember something. I just want to point out something before I move to this one. I get back to the central limit theorem. Look at the distribution of x. The distribution of x was positively skewed, but the sampling distribution of x bar becomes a normal distribution. I'm going to draw it differently here because I'm getting difficulties to draw it on there. The sampling of distribution of x bar is a normal distribution. All right, but look at that. If n is larger, now look at the above. That is the positive skewed. X was positively skewed, but x bar became normal if the sample size is large. That is one of the beautiful thing about central limit theorem. In fact, I don't really need to know what the population distribution is. Even if I did not know that, it would not have been a problem because the central limit theorem shows that in the end, irrespective of what the population might have been, if the sample size is large enough, it will always, the x bar rather, will always be a normal distribution. Even if x, listen to me well, even if x is a distribution that is crazily like that, I don't know what it could have been. I'm exaggerating here, but whatever it could have been, suppose it was something like this, all right? Something like that, for example, or anything else, whatever. It looks like this, for example, or it looks anything. I don't know what it could be. Something like that, or anything. Then what happens is that x bar will still follow a normal, irrespective of what the population might have been. We don't really need to worry about the population shape or the population. We don't need to worry much about it because the x bar will still be normal if, of course, n is large. All right, just something that I forgot to mention in the central limit theorem. Now let me get back to the theorem that I was discussing. This theorem, however, states that if x is normal, this one is different. In the central limit theorem, I don't mention if x is normal. But this theorem here, it says if x is normal. So we are assuming that x is normal, not like the one before which was positively skewed. We are assuming that x is normal. Then the distribution of the mean of size n, the distribution of x bar, this means that the distribution of x bar will also be the distribution of x bar of a certain size n will also be normal, exactly normal with mean mu, the same mean like above, the same mean mu, but the variance is going to be, here the variance was sigma squared, let's suppose, but the variance here is going to be sigma squared over n because of what we just explained. All right, the variance of x bar is going to be sigma squared over n. So the difference between this and the previous is what? Here we are stating that x is normal. If x is normal, then x bar is exactly normal with mean mu and variance sigma squared over n. So, but in the central limit theorem, I don't state if x is normal. All right, that's the main difference. And this is exactly normal, irrespective of the sample size. And bear in mind that it is irrespective of the sample size. Even if a sample size is free, even if a sample size is small, x bar will still be normal if x was normal. All right, even if the sample size is small. But this is not the case for central limit theorem. Central limit theorem, x bar will be normal only if the sample size is large. So that was just a summary of it. And then I gave you some activities that probably this one I will just start it with you. All right, I will start this activity with you, and then we will end the lecture for today. It is assumed that the number of claims arriving at an insurance company per working day has a mean of 30 and standard deviation of 10. So what does it mean? Let x be the random variable representing the number of claims. Do not forget that this is the first thing that you have to do. Let x be the random variable representing the number of claims arriving at an insurance company per working day. It tells me that the mean of the number of client, the mean of the number of client is 30. So the expected value of x, which is also referred to as mu, equal to 30. And then standard deviation of 10. Standard deviation of 10 of x. Standard deviation of x is equal to 10, which is also referred to as sigma. Look at this well. I did not at any point in time wrote x follows a normal with mean 30 and variance sigma. I'm not doing 30 and variance 10 to the squared. I'm not writing something like that. That does not make sense because it is not mentioned here that the claim follows a normal. So this is why you have to be very careful. Don't write things that are not meant to be written, okay? You have to be careful about that. This is why I just wrote it in terms of its notation as it is. A survey was conducted over 40 working days. So we understand that the sample size is 40, which is large according to this course definition, because then it's larger than 30. Calculate the probability that the sample mean, calculate the probability that the sample mean, that is x bar, number of claim arriving per working day was less than 25. Less than 25. That is what is being asked. The probability of x bar. Look at this. We are talking about x here, but now I'm talking about the sample mean is less than 25. This is what I need to do. To be able to do that, I don't have space. I'm going to write it up there. You need to know the distribution of x bar. If you don't know the distribution of x bar, you won't be able to calculate the probability of x bar. But the distribution of x bar is what? It's a normal distribution with mean mu 30 and variance sigma squared over n. Sigma squared is 10 to the squared over n. N is what? The sample size is 40. 10 to the squared over 40. That is how we define x bar. But this is by the CLT. You need to write it by CLT because you have to understand why you got this. Otherwise, it would not. It applies only in the context of a CLT because the sample size is large. So the next step is to do what? When you have understood what the sampling distribution of x bar is, you can start computing the probability of x bar by applying the transformation that I explained to you before. 25 minus 30 divided by 10 over root of 40. And then you calculate this and you will get your answer. Okay, so that's how you would proceed for this one. Now you can go through the proportion on your own. As I told you, I'm going to focus on the mean. Now I would leave this as self-study for you because bear in mind the self-study tag should have been written. I've not written it there, but just for information, this is going to be considered as self-study. This one as well. Of course, if you have trouble, we will discuss it. But if you don't have trouble, we can go on with it. But if you have issues, let me know next time we meet. And then the normal approximation to binomial as well is on self-study, which this one I've already mentioned, which is on self-study. So you can go through these on your own. But for the normal approximation to binomial, just remember something. There is something that we call continuity correction that I want you to understand. Continuity correction. Please ensure that you understand this concept of continuity correction. If ever you have problem with that, I will explain that to you in the class next time we meet. But just let me know if you have issues to understand that. For example, when I say at most 65, when x is at most 65, this is written like that. At most 65, less than or equal to 65. But then I can't work with the x as it is. I have to apply continuity correction. Continuity correction states something. It states that the 65 would have to be either 64.5 or 65.5. So if x is less than 65, the continuity correction states that I need to change this value into either less than 64.5 or less than 65.5. I don't use the 65 because I'm moving from a binomial to a normal, which means that I'm moving from a discrete to a continuous distribution. And each time I move from a discrete to continuous, I have to apply this continuity correction. And the continuity correction will state either I choose 64.5 or 65.5. In this particular example, because I have 65 is included in there, 65 is inclusive, I have to start from 65 to go to the left. I cannot start from 64.5 because if I start from 64.5, I exclude 65, which is wrong. If I would have used 64.5 if x was less than 65, then I could exclude it and use 64.5. But here, because it is less than or equal to, I can't exclude the 65. This is why I can't take 64.5, but I have to take 65.5. So this turns out to be less than 65.5. All right. I could still use less than or equal to. I could use less than. It doesn't matter anymore because now we are working in the continuous case setting. So just an analogy, remember that when we were doing frequency distribution in the first semester, when we were doing frequency distribution, we wanted to draw, for example, a histogram. If a distribution was discrete, what you had to do is to minus 0.5 to the lower limit and add 0.5 to the upper limit, and this will give you new class boundaries. All right, and this is the same principle that is going on here. We are applying a little bit the same principle. This is the continuity correction. So I'll leave it to you to learn a little bit more about it, and also I'll leave it to you to learn more about the Poisson distribution. All right, the Poisson distribution. Just for your information, to apply the continuity correction, to apply the normal approximation to binomial, there is a condition. NP should be greater than or equal to 5, and n into 1 minus p should be greater than or equal to 5. When you're going to study it, just bear that in mind, that these are the conditions that need to be satisfied to apply the normal approximation to Poisson, to binomial, excuse me. To Poisson, the condition is that your lambda, the condition is that your lambda should be greater than 5 for you to be able to apply the the normal approximation to Poisson. We are going to assume that the lambda is greater than 5, then your x will follow a normal with mean lambda and variance lambda. Okay, but this I leave it to you to study on your own. I just gave you some basic idea about it. Okay, some stuff that are important because sometimes some books consider these things differently. Okay, so why I take it like greater than 5 in our context. And then you are going to do this activity on your own, and this activity you have to understand that it's not the central limit theorem as such because the sample size is small. So I will leave it to you to discover what it is. And if ever you are having trouble, of course, we are going to discuss it the next time we meet in class. So I'll stop for the time being. I hope you have understood a little bit about the central limit theorem. And if ever you have any query or if you have any problem, please do not hesitate to let me know. Thank you. See you.